Thanks, folks. This is the Advanced VPC Design and New Capabilities for Amazon VPC session. Or in short, we're going to be talking a little bit about how an Amazon VPC architecture looks like with all of the components that are involved. But then we're going to be diving into all of the new features that have come out over the last 12 to 18 months. So I'm Matt Lewis. I'm a principal developer advocate over here for AWS. And let's get rolling. We've got a whole bunch of stuff to cover. So firstly, let's take a step back in time, and we're going to rewind back to around about November 2018. So in November 2018, we still had EC2 and Amazon VPC, and we've got a region here and a VPC. So a VPC is a region level construct, which you assign a CEDAR address range to. And we're just going to be stepping through how we built out a VPC and that sort of thing. So we've got multiple availability zones, we've got public subnets, private subnets, and then you can deploy EC2 instances inside your subnets in the availability zones, in the VPC, in the region. And so I always use EC2 as kind of like the base level service here, just to use as an example for connectivity and that sort of thing. It just makes a lot of sense. Now, I also think about AWS services being in two different classes or two different types of services, public services and private services. So anything inside the VPC is really private. It's a domain that you manage and control. But anything outside of the VPC is generally public unless you build a private connection to that service. So S3, DynamoDB, Lambda, SQS, SNS, all of these services are all public services out in the public AWS realm. So when we're communicating inside the VPC, we'll actually use route tables that are assigned to subnets. Now, the route tables basically give you control over everything that's going on inside the VPC, so where traffic can communicate to and that sort of thing. So here we've got a couple of route tables on the left-hand side. We're just going to build out what an advanced VPC architecture looks like, and routing is really the key here on how we communicate with everything else. So we'll start here with an internet gateway or an IGW. The internet gateway gives us access to public services and also the public internet, and we just build a default route to the IGW. We have an elastic IP assigned to our instance A here, and we can then communicate with all of these public services and also the public internet. Now, for our private subnet, we can actually send traffic via a NAT instance instead of natively talking directly to the public internet. And then the NAT instance has the ability to communicate with the public internet, or you could also use NAT Gateway, which is a scalable NAT service that sits inside the VPC as well. And so we build out our routing on the left-hand side here. You can also talk to S3 and DynamoDB privately using VPC endpoints, and we'll use prefix lists there to communicate privately. And a VPC endpoint is almost like a bridge between, say, S3 and your VPC, or DynamoDB and your VPC. Then we might want to connect to our on-premises. So we'll use Direct Connect or VPN, maybe some Direct Connect Gateway. We can peer our VPC with other VPCs directly in a point-to-point fashion, either within a region or across to another region. And you'll notice we built out our routes on the left-hand side here again. We've got Transit Gateway, which was a service that was launched in about November 2018. And Transit Gateway allows you to connect to many VPCs. So up to 5,000 VPCs can communicate to each other over a transit gateway. And we can also use VPN from an on-premises to a transit gateway. We've also got Private Link. Private Link is going to enable you to configure SaaS services and that sort of thing inside a VPC that we call a service provider VPC, or you can connect to a bunch of services via Private Link. So any other services outside of S3 and DynamoDB, when you can communicate to those privately within the VPC, it's generally using a Private Link enabled service or an interface endpoint. For metadata of traffic going in and out of the VPC, we can use VPC flow logs. And then lastly, we've got Global Accelerator up here on the left-hand side. And Global Accelerator is like an Anycast service. It's much, much more than that, but it basically allows you to front things in the VPC at our edge locations using Global Accelerator. Now, what you see here is really what is a combination of a whole bunch of different networking components, but customers are basically building this architecture that you see in front of you, or a combination of these services depending on what they want to build. Some customers use Direct Connect, some use VPN, some use IGWs, some use flow logs, some don't. So it really does depend, but this gives you a bit of an idea of what an Amazon VPC architecture looks like. So what we're actually going to do now is take this architecture and then take a step forward in time and talk about all of the new features that have been released over the last 18 to 12 months. So firstly, what's changed? All right, let's start with interface VPC endpoints. So an interface VPC endpoint is where we've basically got a whole bunch of different services that exist in the public realm. So I'll take one, for example, maybe the AWS EC2 API. For the longest time, the AWS EC2 API was actually, it resided within the public realm. So whenever you wanted to do an API call from an EC2 instance within the VPC, you'd have to go over an internet gateway out into the public realm. Now, interface endpoints, or endpoints that are powered by private link, enable you to have these services dropped into a VPC privately. So each of these services can have an interface endpoint, and we just drop a set of endpoints into that VPC, and then we can reach those endpoints natively in the VPC. So what basically happens is we have a whole bunch of Elastic Network interfaces that we create and front these services with inside the VPC. And each of these Elastic Network interfaces will take an address from the VPC range. So you'll notice here on the left, we actually don't need any routes to each of these services. You can reach them natively via these Elastic Network interfaces. So previously, we had about 18 services that were supported over private link, which is quite a lot. But in the last 12 to 18 months, we've actually been pretty busy with VPC endpoints, and we now have over 52 services that you can drop into a VPC privately using private link. And so this is actually awesome. You've seen this kind of shift away from all of these public services and having to have an internet gateway to privately connecting to all of these services from within your VPC using private link enabled endpoints. We also released endpoint policies as well, so you can add a little bit of policy control around the endpoints and who can talk to services and that sort of thing. Okay, so we also made some updates to VPC endpoint services. So a little bit different from interface VPC endpoints. So VPC endpoint services is where you can use private link and take a SaaS VPC here on the right-hand side, or what we call a service provider VPC. So you might have like a SaaS application running in that VPC. And then you can use private link or a VPC endpoint service to connect to a network load balancer, and your SaaS application, for example, is the target of the NLB. So traffic flow goes from the customer VPC over the private link enabled endpoint through to a network load balancer and through to your service. So it's a pretty easy way to drop this service into multiple VPCs if you wanted to privately. So we now have tagging for endpoint services. Seems like a no-brainer, so pretty happy that one's there. Endpoint services are also reachable over intra and inter-region peering as well now. So when we've got a VPC and that VPC is peered to your customer VPC that has the endpoint in it, you can actually reach from that VPC all the way through to the endpoint and all the way through to your service provider VPC. Now, this is actually applicable for the other interface endpoints that we had for all of those other services. So you could effectively have a VPC that has all of these endpoints that exist within that VPC, and then connect through over peering or transit gateways, or maybe even over Direct Connect or something similar, and reach out to any of those services. Pretty cool. Okay, let's move on to Global Accelerator. So if we look at Global Accelerator, basically we've got your Amazon Edge locations, and Global Accelerator operates at the edge, or that's where it sits. So we've got an Anycast IP address here. You can think about it like Anycast, but it's a lot more than that though, really. We've got a 310.3.125, and we've got our users that come in and access that Anycast IP. Global Accelerator is actually going to direct you down to your elastic IPs of your service. In this case, it could be a network load balancer that's fronting some applications inside that region. And so these users, when they use that single IP to access the service, will actually get routed to the closest region. So now with Global Accelerator, we've got a whole bunch of additional application endpoints in additional regions. So you can use Global Accelerator to connect to additional regions. We've got source IP preservation of the client IP. So previously, when you connected from your clients down through to your application, the application couldn't see what the source IP was. Now we have source IP preservation, and we now have support for EC2 endpoints, where we can basically drop Global Accelerator into a VPC privately using an interface endpoint, allowing access privately from Global Accelerator down into your VPC. Okay, let's talk about AWS SitetoSite VPN. So SitetoSite VPN is basically where we've got a virtual private gateway, or a VGW, which is attached to a VPC. We've got our on-premises, or what we call the CGW, which is basically another term for a CPE, customer premise equipment, or a router that sits at the on-premises site. We've then got the public internet, and we can connect via IPsec tunnels through to the VGW. And this is what we call site-to-site VPN for an Amazon VPC. So now we support certificate authentication for site-to-site VPN. So previously, you would have a pre-shared key, which you would have to share with your CGW when you're configuring the CGW for the IPsec tunnel to come up or to be established. But now we can actually use AWS Certification Manager. We create a certificate, we configure the CGW, and then we use the certificate on the CGW to connect through to the VGW or establish the IPsec tunnel. So in this case, we're creating a customer gateway, and we've got this option now to select the certificate ARN that we've created using AWS Certificate Manager. We now support IKE v2, which that's been a long time coming, so I'm pretty happy with that one. And we now allow you to configure the security algorithms and timer settings of the IPsec connection, which is not something you could previously do. So you can see here, there's a whole bunch of options that we can do here. We can choose AES 128 or 256, SHA-1, SHA-2, 256, etc., etc. Now, as part of the Transit Gateway launch, we had some folks actually build a tool to migrate from site-to-site VPN to AWS Transit Gateway, where Transit Gateway actually supports VPN termination or VPN connectivity. So this tool can actually help with migrating from site-to-site VPN if you started to use a Transit Gateway. Okay, let's talk about AWS Client VPN. So Client VPN is where we built a client VPN service to allow you to have a client on a laptop or similar, which can connect through to this service, and then we can drop that connectivity through to an Amazon VPC. So we've got a user here using an OpenVPN client. We've then got a TLS-based tunnel over the internet connected to the client VPN service, and then we attach that client VPN service through to an Amazon VPC. And so what this also allows us to do is connect from your client that's running the OpenVPN client through the client VPN service into the VPC and down through to other VPCs, the internet, over things like an IGW to S3 or DynamoDB or others, over a VGW back to an on-premises if you wanted to. So the client VPN is really used as a jump point or an access point into a VPC that then could be used to access other things in AWS or elsewhere as well. So some of the updates for Client VPN, we now support CloudFormation for Client VPN. That one's definitely a no-brainer, so I'm pretty happy that that one's there now. We now support split tunneling, so not all traffic is going to go over the client VPN service to AWS. You can split other traffic out to other destinations as well. So maybe traffic that's not destined towards AWS, you can send it via the split tunnel. And we also support multi-factor authentication for Active Directory now. And we have a new desktop client for Client VPN, which is quite recent. All right, let's talk about AWS Transit Gateway, one of my favorite services. And we're going to throw in some Direct Connect and some Amazon VPC in here as well. So Transit Gateway, what is it? Well, Transit Gateway is really a logical routed entity which allows us to connect to many VPCs. So in this case, we've got three VPCs, VPC1, VPC2, and VPC-N. Now, N could be up to 5,000 VPCs. So we can have up to 5,000 VPCs attached to a Transit Gateway. We can also then take our on-premises and connect via VPN to the Transit Gateway. And in a lot of cases, which is interesting, we're actually seeing the Transit Gateway be used as a connectivity point for Transit VPC. So we actually built Transit Gateway to help with customers that were building Transit VPCs, so they wouldn't have to build Transit VPCs anymore. But what we actually saw was folks that wanted to deploy some firewalls in line or maybe a WAF or something similar inside a VPC have actually started using Transit Gateway with IPsec, with BGP, and ECMP or equal cost multipath across multiple appliances within a Transit VPC. So ECMP was definitely the big gain there, where you can now actually auto scale a Transit VPC edge and use ECMP to load balance across multiple VPN connections across multiple instances in a Transit VPC. Pretty awesome stuff. And so some of the updates to Transit Gateway, we now support Direct Connect connectivity. So in this case, we've got a AWS Transit Gateway that's connected to a Direct Connect gateway. And then we take our on-premises and we use something like a Direct Connect connection. And we use what's called a Transit Virtual Interface or a Transit VIF. Now, the Transit VIF is something that each Direct Connect, whether it's if it's greater than 500 meg, so a 1 gig, a 2 gig, a 10 gig, etc., gets a single Transit Virtual Interface. So whereas you might get 50 virtual interfaces, either public or private, you can now have a single Transit Virtual Interface which can connect through to a Direct Connect gateway and connect to your AWS Transit Gateway. All right, so let's take a quick detour on AWS Direct Connect. Now, if Transit Gateway is one of my most favorite services over here at AWS, I would have to say Direct Connect is my second favorite. Don't tell the Direct Connect product team I said that, though. So with Direct Connect, and we're just going to do a really quick overview here, we've got our on-premises on the right-hand side, which we might have a 192.168.0.0/16 as our on-premises IP range. We've then got the AWS region on the left-hand side, and we've got our public services that we had before, so S3 and Dynamo and Lambda and others. And then we've got our VPC in the AWS region. And the idea here is with Direct Connect, we want to actually bridge your on-premises to your VPC privately. So in this case, we've got our service provider network, which a lot of companies, enterprises, etc., would use something like an MPLS IP VPN or a DWDM or a VPLS, and basically use that WAN to connect all of their sites together. So in this case, we're using the WAN or the service provider network to connect from the on-premises to an AWS Direct Connect location. So a Direct Connect location is where we've deployed points of presence. So routers at a physical location that you can plug a fiber into. So we've got our AWS cage, which is in the Direct Connect location. We've got our routers inside the AWS cage. We've then got either a customer device that you deploy, so something that can be used to terminate the Direct Connect from AWS, or you could use a partner. And we've got a whole bunch of partners. Last time I counted, it was in excess of 150 different partners globally. And this is where partners have deployed equipment at our co-location facilities so that you can plug into that partner device without having to deploy a router yourself. So we've got the WAN network connected to our customer or partner device. Then we build a cross connect, and the cross connect is essentially just a physical fiber. It's a fiber that goes from your AWS cage to your customer device or partner device. And then once we've got that cross connect, and a cross connect is essentially connected to a Direct Connect port, and Direct Connect in itself, the service itself, is really just a port on a router that you can then create VLANs on, so virtual interfaces. So if we think about the private connectivity piece, we build what's called a private virtual interface from the VGW, and it's the same VGW we were using for VPN termination before, we now connect a VLAN or a private VIF to that VGW on the left-hand side, and then on the right-hand side, it's just a VLAN or sub-interface on your customer or partner device. Now, if we wanted to connect natively to some of the public services, we can build what's called a public virtual interface. So a public virtual interface is basically going to give us access to S3 and Dynamo and those services public. Now, a public virtual interface is a little bit special in that it advertises all of the public region routes for every region in AWS globally. So you'll get about, last time I counted, it was about 1,900 BGP prefixes advertised over a Direct Connect public virtual interface. And we actually do use BGP as the routing mechanism to advertise routes from AWS to your on-premises via the virtual interfaces. Okay, so the cross-connect or the Direct Connect service also allows you to create multiple virtual interfaces. So we can have up to 50 virtual interfaces on a Direct Connect. And in this case, we've actually got one public VIF and we've got two private virtual interfaces now. So we're connecting to two different VPCs. So we can have up to 50 private or public virtual interfaces. And what we generally see is customers having one or two public virtual interfaces and then many other up to 48, 49 private virtual interfaces connected to 48 or 49 VPCs. Now, each one of these private virtual interfaces actually has a BGP session back to the customer or partner device. So what we actually realized was customers were building out a whole bunch of VPCs, and every time they built a VPC, they had to then go onto their customer device, or the partner would have to go into the partner device and configure a new virtual interface, a new BGP session, etc. So we built this service called Direct Connect Gateway. And what Direct Connect Gateway allows us to do is basically take a private virtual interface, connect that to the Direct Connect Gateway instead of the VGWs, and then the Direct Connect Gateway can attach directly to VGWs natively. So in this case, we've just got one private virtual interface, and we can have up to 10 VPCs on the left-hand side here connected to that Direct Connect Gateway. So it's giving you a little bit more scale beyond the 50 private virtual interfaces. You can now get up to about 500 VPCs connected through one Direct Connect connection. Now, one of the important features around Direct Connect Gateway was actually the ability to have Direct Connect Gateway connect across multiple regions. So Direct Connect Gateway is one of those unique global services. So here we've got a private virtual interface. The Direct Connect is homed to region 1. We're using Direct Connect Gateway, and we can also attach VPCs in other regions. So you could be connected in, say, our San Francisco region, but then have another VPC in our Dublin region connected to that same Direct Connect Gateway. And the communication between the Direct Connect Gateway and the VGW in the other region is actually going to go via the AWS backbone. So we've got two separate regions here. Okay, so for the longest time, we actually couldn't have our VPCs connected to the same Direct Connect Gateway in different accounts. So up until late last year, that was the case. But then we launched multi-account DX Gateway. So we can actually take the DX Gateway and we can drop that or connect it to multiple VPCs in different regions, but those VPCs could be in separate accounts as well. Now, also up until late last year, our partner connection speed, so this is when you're using a partner device at the co-location facility, we could only go from 50 meg up to 500 meg. Now, after we launched this feature, you can now go up to 10 gig of partner connectivity. So 1 gig, 2 gig, 5 gig, or 10 gigs of capacity when using an Amazon partner. And our customers are actually really happy about this because they can use a partner for a 5 gig connection, for example, and not have to deploy those devices at the co-location facility. They can just use a partner's set of devices there. Okay, we touched on this a little bit earlier when we were talking about Transit VPC. We did late last year release the ability to have a Transit Gateway connect to a Direct Connect. So when Transit Gateway first launched in November 2018, we had VPN capability to connect to your on-premises. And that was great, but a lot of customers do use Direct Connect. So in this case, what we can actually do now, we've released this new type of VIF, and for every physical Direct Connect, you can have an additional VIF. So we could do 50 public or private VIFs before. We can now do 51 VIFs, and one of those virtual interfaces can be a transit virtual interface. And the transit VIF actually attaches to a Direct Connect gateway. And so from the Direct Connect gateway, we can then attach to a transit gateway, which can then attach to up to 5,000 VPCs. So now instead of having 10 VPCs connected to a Direct Connect gateway, you could have 5,000 VPCs connected to a Direct Connect gateway through the transit gateway. So pretty amazing stuff. The scale here that we've built out for Direct Connect and transit VIFs is just immensely huge. And so it gets a little bit better than that as well, in that you can actually have up to 3 transit gateways connected to the same Direct Connect gateway. So in this case, we could, in theory, have up to 15,000 VPCs connected through a single Direct Connect connection. Now, again, a Direct Connect connection is a physical means. That cross connect is a physical fiber. When you start working at that kind of scale, you probably want to have multiple Direct Connect connections and have some form of redundancy across those, so that if you lose that Direct Connect connection, you don't lose all that access from your on-premises all the way through to the 15,000 VPCs in this case, which is a huge amount of scale. Now, one of the key pieces here, and it's the same with just Direct Connect Gateway, we've actually decoupled all of these VPCs from the Direct Connect itself. So when you can now spin up and spin down these VPCs as you like, and you don't have to go and reconfigure the customer devices here as you did with the original private virtual interface architecture. Okay, so that was Direct Connect. Now I want to talk about Amazon VPC route limits, and this was actually something I was really passionate about for a couple of years here. The default limit within a VPC for routes in a route table was actually 50 for the longest time, and the hard limit was actually 100 routes. And to me, when I'm thinking about transit VPCs and the transit gateways, and transit gateway can do up to 10,000 routes, and you might have a whole bunch of scale that you're building with connectivity to a VPC. 100 routes inside a route table is actually quite small. So late last year, we actually released the ability to do 1,000 routes in a route table for a VPC. So this is actually pretty awesome. Now, 1,000 might not sound like much versus the transit gateway's 10,000, but when you think about a single VPC and 1,000 routes, you probably don't want to go much further than that, just because of the complexity to manage all of these routes. But 1,000 is definitely much, much better than 100 routes that we had previously. And this is available on request. So not something that we'll just up your limits to natively. You can open a trouble ticket and we can go in there and increase your VPC route limits if you needed more than the 50 default or 100 hard limit default. We can go to 1,000 now. And that one's been something I've been looking forward to for a long time. I had a lot of customers that wanted to go beyond that 100 route limit in a VPC. Okay, let's talk about Ingress Routing. This is a new one late last year, and this is it's a little bit different on how we're doing routing within the VPC, because when you look at a VPC, the route tables were really just for routing of traffic as it pertains to inside the VPC. So before Ingress Routing, we actually have multiple instances here, and we've got our route tables with all of our destinations for each of these route tables for each of the subnets here. So again, always a good idea to create multiple route tables, one per subnet. And so when traffic comes in via an internet gateway, what's going to happen is, and let's just say our destination here is instance B, or maybe instance A, we're actually going to follow the local route of the VPC. So that's that magic 10.1.0.0/16. And this route is actually created by Amazon when we create a route table, and it's equivalent to the VPC range that we configured when we created the VPC. So everything's just going to get routed naturally within the VPC. So what we can actually do with Ingress Routing now is we've released the ability to, or we've enabled the ability to have gateway route tables. Now, a gateway route table is where you've got a route table associated with not a subnet, but an internet gateway or a virtual private gateway. So in this case, we've got traffic that's destination is B, so our instance B that we had earlier. But instead, we're going to say, as traffic comes in an internet gateway, let's direct that traffic over to a firewall, which is actually instance A. So we're doing some routing. Instead of just following that local route in the VPC route table, we're actually doing a little bit of ingress routing at the internet gateway. So instance A can then forward traffic onto instance B as needed. Now, if we look at the virtual private gateway, we've also got a destination of B, traffic's coming into the VGW, and we're sending that to firewall A, and firewall A is then sending traffic on to instance B. So ingress routing really gives you the ability to have something like a firewall or a WAF or some kind of appliance in line from the outside inbound to your VPC. You could always do this outbound. So you could say, okay, instance B going to the internet, please go via a NAT instance or something similar. But now we have the ability to do this inbound on an internet gateway and a virtual private gateway. Pretty cool stuff. All right, that was a little bit of a shift. We talked about some Direct Connect stuff, and remember my second favorite service in AWS. And we also talked about some ingress routing stuff and our route table limits. Let's go back to AWS Transit Gateway now. So with AWS Transit Gateway, we also released accelerated site-to-site VPN, and this was a new one late last year at reInvent as well. So we've got a Transit Gateway, we've got our VPCs attached to the Transit Gateway, and again, we can have up to 5,000 VPCs attached to the Transit Gateway. And then we've got our on-premises, we've got our VPN connections from our on-premises to the Transit Gateway, and these VPN connections actually traverse the public internet. So the Transit Gateway will have a couple of IPsec endpoints that are advertised out to the internet, and you'll connect to those using IPsec. This is basically how VPN connectivity works to a Transit Gateway. Now with accelerated site-to-site VPN, we're taking that same architecture, but we're actually adding Global Accelerator into the mix so that we can use our edge locations. And so our two IPs that we would connect to for our VPN connectivity previously directly on the Transit Gateways, those IPs are actually advertised like Anycast IPs out of our edge locations. And now when you connect from your on-premises, you're actually going to an edge location that's close to you. And so what happens then is we're using the AWS global network from the edge location to the Transit Gateway. And so we capacity manage our backbone and a whole bunch of other good stuff, as opposed to you just going over the native internet. So in this case, we're combining AWS Global Accelerator with VPN connectivity to a Transit Gateway. And that's going to give you maybe some lower latency, some reduced jitter, and a more consistent connection because you are going over that capacity managed piece of the AWS backbone between the edge location and the Transit Gateway. And this is really ideal for if you've got a lot of sites globally and you want to connect back through to a Transit Gateway, you can take advantage of the AWS backbone here. Okay, another new service here. We had a whole bunch of stuff that we actually released towards the end of last year around Transit Gateway. And Transit Gateway has been an immensely popular service for us. We've got a whole bunch of customers using it. It is amazing. And we've been, you can see that by the new services that we've been adding on to Transit Gateway. So now we've got AWS Transit Gateway Network Manager. So when I talk to customers, one of the complaints around networking that I've heard quite a lot is, hey, I really want to get visibility into traffic going over my network. I'd like to get visibility into how many connections I've got, both Direct Connect and VPN, and what the status is. The visibility piece, traffic mirroring, which we'll talk about. I've got some traffic mirroring slides coming up shortly, and also VPC flow logs give you visibility in the traffic going over your network, but you didn't really have a good mechanism to view all of your connectivity components when it comes to your connectivity architecture. So AWS Transit Gateway Network Manager is going to give you the ability to manage and monitor your global network that basically constitutes all of your connectivity to AWS. Now, we've also integrated with a whole bunch of SD-WAN partners and their branch appliances. We'll talk a little bit about that. But the whole idea for Transit Gateway Network Manager is to give you visibility across AWS and the whole branch network that's connected back to AWS. Okay, so we've got a really quick screen here. We've got our global network on the top left-hand side here. And so you can see that it's made up, in this case, of 5 transit gateways. We've got 16 sites. We've got 50 devices. And that's just going to be a really quick summary of what your global network inventory is. Then we've got some VPN status to our transit gateways. So you get some statistics there on the status of your VPN connections. And then we've got our network event summary. So this is when there's been some topology changes or status updates or routing updates around our connectivity to AWS. And so what I really like about Network Manager is this visualization here. So we've got our global network topology. We've got our global network topology, and it's going to give you an overview of all of your transit gateways, all of your VPCs, all of the connectivity, DX and VPN, et cetera, that's going to connect through to your AWS deployment. So you get a bit of an overview here on what everything looks like. Pretty awesome stuff. Now, SD-WAN has been one of those services that a lot of our customers have used to connect their branches back to AWS. We did also work pretty extensively with folks like Cisco, Silver Peak, Aruba, Aviatrix, when we were building Network Manager to integrate their stuff around SD-WAN into the Transit Gateway Network Manager as well. So definitely something that's worth checking out. All right, so that was Network Manager. Now I've got 2 last features for Transit Gateway. One of those is Multicast. So we now can do multicast within a VPC using Transit Gateway. And I've got a quick link here if you want to learn more about how multicast works with Transit Gateway. Definitely worth checking out if you're interested in multicast. But also inter-region peering. Now, inter-region peering was one of those things that customers really wanted to take advantage of our AWS backbone, and you might have multiple transit gateways in multiple different regions, and inter-region peering really helps with that. So if we dive into inter-region peering or cross-region transit gateway peering, we've got 2 transit gateways. They're sitting in 2 different regions, and essentially this is just static peering between the regions and between the transit gateway. So we've got a transit gateway here on the left that could be part of a region, and we've got another transit gateway here on the right that could be part of another region. And we're just going to configure static peering between those 2 transit gateways. Now, this is a new attachment type, and we're also using the same encryption that we use for VPC peering between the regions. But it's basically going to be a mechanism to connect transit gateways together. Now, a quick point here, we don't actually support transit gateway peering within the same region. Now, there might be a reason to do that, but really this feature is geared towards connecting transit gateways from one region to another. Now, this is just static point-to-point peering. We can actually go a lot further than that with transit gateway peering. So in this case, if you've got many regions with transit gateways in each region, we can actually connect all of these transit gateways together in a full mesh topology. And now you've basically built a global backbone connecting all of your transit gateways on top of the AWS backbone. This is really, really cool. Now, one of the things you do need to consider here in that when you're connecting transit gateways together, we're basically using peering as a static mechanism to connect transit gateways together. So you basically determine how the routing works and that sort of thing. But we do also ask that you configure unique ASNs or autonomous system numbers for each transit gateway when you're creating the transit gateway. So they do need to be unique. And we're actually asking for that because we might do something with dynamic routing and that sort of thing with transit gateway peering in the future. But this mechanism is actually really amazing that you can build your own backbone between all of your regions, and it's all private connectivity from one transit gateway to another. And each region could have, or each transit gateway in each region could have up to 5,000 VPCs, and you can just peer them across to every other region here. Pretty awesome stuff. Okay, let's take a dive into VPC traffic mirroring. So we've talked about transit gateway a whole bunch, and you remember one of the questions customers have been asking us is, how do I get visibility into my traffic inside of VPC? Now, we've got VPC flow logs, but flow logs are really just metadata. for a particular time period. What customers have been asking for is the actual packets, the actual traffic going to their instances, and traffic mirroring brings this to the party. And we released traffic mirroring at Reinforce last year. There was a big fanfare as part of the launch, so I'm a little bit excited and biased about this one. So here we've got an instance and we're receiving traffic and sending traffic over an internet gateway. And so what we can do now is create a traffic mirroring session. And then what will happen is the packets from or to and from that instance now get mirrored over to a monitoring instance or to another ENI. So now we're getting a copy or a duplicate of those packets that are going in and out of that EC2 instance. So in this case, we're sending everything inbound and outbound. Okay, so when we think about traffic mirroring, there's three different components. There's the target, which is really the destination for the mirrored traffic. There's the filter, so you don't have to receive all the traffic, and we'll talk about how you can filter that down. And then there's the session. We can have multiple sessions per EC2 instance to send traffic to different destinations based on a few different attributes. So let's start with targets. So VPC traffic mirroring can be sent to either an elastic network interface or a network load balancer. So if we wanted to just send traffic to a single monitoring instance running, say, Zeek or Suricata, some open source IDS tools, we can do that. Or if you wanted to build some scale into the system here, we can actually put a network load balancer in front of our monitoring instances, and we'll talk more about what that looks like. So you can also set a number of rules that define the traffic that's to be copied to the mirrored session. So in this case, we've got traffic coming in and out of the EC2 instance. We've set a filter for traffic mirroring to say we're only interested in inbound packets. So inbound packets are going to be sent from that EC2 instance to the monitoring instance, and we're actually not going to mirror the outbound packets. So when we look at filtering, there's a couple of different options here like flow direction, protocol, source IP, source port, destination IP, destination port, and one of the more important ones here is truncation. So we can take a sampled truncated packet instead of the full thing. And so when we tie all this back together to a particular instance, we actually build what's called a session. So a session is going to be a relationship between the traffic mirroring source and the traffic mirroring target and associated with the appropriate filter. So there's three components: the source of the packet, so what instance we're mirroring traffic from, the target where we're sending it to, and then the filter, how much traffic would we like? Do we want to truncate it? What source port, destination port, et cetera, et cetera. And so each traffic mirroring source can support up to 3 sessions. Now this gets a little bit interesting where you can basically set a priority here with your session. So the priority the session with the lowest priority will have with the lowest ID will have the highest priority, and a packet only gets mirrored once, but basically you can do a little bit of rule matching here on where you actually want particular packets to go to. So what maybe Zeek and Suricata instance, for example, you could have multiples of those depending on the source and destination. Okay, so let's talk a little bit more about scale with traffic mirroring. So in this case, we've got a whole bunch of traffic going to an EC2 instance. We enable traffic mirroring, and we're sending traffic, in this case, to a network load balancer. And so we've got multiple monitoring instances in an auto-scaling group now that are receiving the packets from the network load balancer. So the right sizing we talked about before, you can do a little bit more scale than just having a single instance and right sizing that. You can actually have a fleet of instances as monitoring instances receiving traffic from many instances on the left-hand side here. And so we could set an auto-scaling rule to say, hey, based upon certain metrics, let's scale out this fleet of monitoring instances as well, just like you would with a normal network load balancer and auto-scaling. So what do you actually do with the packets once you receive them? So here we've got a monitoring instance, and we actually partnered with a whole bunch of APN partners that have traffic inspection applications and the like. You can deploy those as monitoring instances as the source or the receiver of the traffic mirroring packets. You could also build your own network analyzer. So you could use open source tools. We have seen customers say, hey, I actually want to take a packet and do something specific with that and write an application to do things with that. Or you could use Zeek and Suricata to deploy open source IDS and IPS tools on your monitoring instances as well. So we've actually got a link here for working with some open source tools, so just how you could do that and use Zeek and Suricata, et cetera, to do that. Okay, let's dive into a quick Amazon VPC traffic mirroring use case. And this is actually kind of cool. It's a bit of a Rube Goldberg machine, but pretty awesome stuff too. So we've got an instance here that's receiving traffic, and there might be bad traffic coming into the instance. Now, it's up to you to define what bad traffic is. But Amazon Guard Duty might fire an alert based upon the traffic that's seen to this instance. And so it'll fire an alert to Amazon CloudWatch events, which will trigger a Lambda event. So it'll match the alert and then identify what the instance and ENI is that needs monitoring. And then Lambda can go and spin up a monitoring AMI or monitoring instance and enable VPC traffic mirroring. So now traffic is going to get forwarded to the monitoring instance based upon an alert that was fired from Amazon Guard Duty. So then we could use Zeek or Suricata or something similar to create logs of the traffic and maybe ship those logs off to S3. Now we could then at a later stage come through with Amazon Athena and inspect the logs and do something with that traffic. Now, let's just say the bad traffic goes away, or maybe we've applied some filters or something similar. You can then have Amazon or AWS Lambda spin down the monitoring instance and turn off traffic mirroring, and everything goes back to normal. And this could all be automated, which is pretty amazing. So a couple of quick considerations with traffic mirroring. So mirrored traffic isn't subject to the outbound security group. So when you apply a security group to an instance, it doesn't actually apply to the mirrored traffic. And also flow logs won't capture mirrored traffic. Mirrored traffic is considered outside of that normal flow in and out of the VPC. It's part of the traffic mirroring service, so you won't see that in flow logs. And packets will only get mirrored if they pass the inbound security group or ACL. So if the packet doesn't make it to the instance, we're not going to mirror the packet. Okay, so that was a VPC traffic mirroring. Pretty amazing stuff. And that one's actually been a long time coming. I've been looking forward to traffic mirroring since I first joined Amazon all those years ago. Pretty awesome we have that now. All right, so we've got a little bit of a divergence here. We've got AWS Outposts, and we're specifically going to dive in on the AWS Outpost networking piece. So Outposts is really where we're taking the technology in an AWS region and we're allowing you to then have that within your on-premises in the form of a rack or multiple racks. It's pretty awesome stuff. So we're basically bringing the technology that we built inside an Amazon region and we're allowing you to have that within your on-premises data center. So we're using the same AWS designed infrastructure, think servers, switches, etc., all in a rack that operates on premises. Now, it is a fully managed service, so we do need always on connectivity back to the region, and that's an important thing we'll talk about. But it does take away all of the management of the underlying hardware that you would normally do in your data center. Now, because it is a fully managed service, we're then extending an Amazon VPC to that service, and you get this single pane of management through the AWS CLI or through the AWS console to manage your VPC that now resides inside the Outpost as well. Awesome. So let's talk about AWS Outpost networking and specifically what the networking components look like. Okay, so we've got our AWS region here, just like we did before in some of the earlier slides. And we've got our Amazon VPC with our VPC CIDR range and our instances A, B, C, D, our different subnets that are in different availability zones. And a subnet is an availability zone construct, and this is prior to Outpost. And so what we do with Outpost now is we are actually extending that VPC all the way through to the Outpost, which is operating on premises. And so now we can create Outpost subnets. And an Outpost subnet resides or exists within an Outpost, but it's in the same VPC that you were using in the region. So now we can deploy some EC2 instances in our Outpost subnets that we've just created. And we can use route tables, security groups, and network ACLs, the same networking constructs that you would have used in the region with your instances inside your availability zones, you can use those inside the Outpost as well. So we've just created or extended that same capability to the AWS Outpost. And so when we think about things from a traffic flow perspective, we've got, say, instance Y or instance Z communicating with each other within the Outpost. And that seems to make sense. I mean, that's the logical conclusion here. Instances talking to each other in the same VPC inside the Outpost communicate natively and directly. But we can also have something like instance Y communicating with other instances inside the region. So instance Y could be talking with instance B or instance D. And so if we have a look at the route table real quick here, we've again got that 10.100/16 local route in the Outpost, just like we did in the VPC in the region. So that route is going to enable everything inside the VPC to communicate with each other. And so we can actually take it one step further, where we've got the internet out through the region or an internet gateway. We've got our public services again, your S3s, your Dynamos, your Lambdas. And then we can build a default route from the Outpost through to an IGW, or we could use VPC endpoints, Transit Gateway, VPC peering, a VGW, and we basically just build out our routes within the VPC just like we would with all of these constructs in the region. Now, the only difference here is something like a Transit Gateway is an immensely scalable service, which we touched on earlier, and the underlying infrastructure that supports Transit Gateway is just massive. Now, that actually runs in the region. So when we're communicating from instance Y inside an Outpost, we're going over the service link or the underlay here, but the overlay is actually the VPC. And then we go out the Transit Gateway in the region. So the Transit Gateway in this case is a region level construct. Now, really quickly, if we had two VPCs, we could then deploy two subnets in those two separate VPCs in the Outpost, and we could actually use peering locally in the Outpost. So peering is one of those exceptions there, but Transit Gateway and VGWs and IGWs all operate inside the region, but we can communicate with those. Now, one of the main purposes of having an Outpost is to connect through to your on-premises workloads. We've now developed this new gateway called a local gateway or an LGW, and that's going to allow us to have a route to the LGW and then communicate to on-premises workloads or anywhere else. Now, one key point here is we use what's called a customer-owned IP range to assign elastic IPs to instances in the Outpost at the LGW. So if you're familiar with the way the IGW works, and we covered that briefly at the start, basically we assign elastic IPs at the IGW just like we do with the LGW, and there's a NAT function that happens there from the instance out through to your on-premises workload. Okay, so let's talk about WAN connectivity for the Outpost really quickly. So we've got our region on the left, we've got our VPC, we've got our customer premises, we've got our Outpost networking devices, which are basically like top-of-rack switches, but they're a little bit more than that because they do BGP and LACP and a few other things. And they communicate via this blue segment to your local network, which we just referenced from the LGW or anywhere else. But then we've also got this service link infrastructure range, which you'll also assign to an Outpost. And that subnet or that VLAN for the service link needs connectivity back to AWS. So here we've got a custom edge router, we've got a WAN connection, we've got a direct connect. And in this case, where we want public access back to the AWS region, so we're using a cross connect with a direct connect, and we're using a public virtual interface for direct connect. And whenever we use a public virtual interface, we do need to use network address translation to public IPs, or you could have this service link range as a public range, but it's probably burning a few more IPs than necessary because we need a /26 here, or you could do port address translation here on a single address, as the Outpost will initiate that communications out over the direct connect and over the public virtual interface to what we call the Outpost service or the Outpost anchor that operates in an availability zone that you choose to home the Outpost to. We could also use the internet because the Outpost service is fronted by Amazon public IP. So you don't actually need to use Direct Connect to connect back to the region when you're using an Outpost. You can just use the public internet if you wanted to as well. And so this is going to then allow us to have AWS control plane traffic connected through to the Outpost, and then also data plane traffic. So from the Outpost service, we've got a data plane connection. And what's going to happen here is traffic's going to be sourced or destined to an EC2 instance in the Outpost. It'll traverse this infrastructure subnet or the service link over the anchor and then get dropped down into the VPC in the region. So this is how we make the VPC look like it expands from the region to the Outpost. And so that's all the content I have for you folks today. So I've thrown a couple of references in here, and we talked about updates for VPC endpoints, so things like access over VPC peering. We've got a whole bunch of new services that support private link interface endpoints. Global Accelerator now has source IP preservation, multiple or additional regions, instance endpoints into a VPC. We had a whole bunch of updates to site-to-site VPN and client-to-site VPN. So pretty amazing transition there on the new features that we can use. And for Direct Connect, DX, and VPC routing, there was a lot of additional features. So we really doubled down on a whole bunch of stuff that we can do here with Direct Connect, DX, and VPC routing. The 1,000 routes per VPC is amazing. Transit VIF really allows you to connect your on-premises in a scalable way to a whole bunch of VPCs in the region. Network Manager, Multicast, cross-region peering, a couple of links here for you folks as well. And then VPC Traffic Mirroring, which has been a long time coming. I'm excited about that one. And AWS Outposts, which is a whole shift in the way we do things here at AWS. And we're thinking about things like distributed cloud and really extending AWS out to your on-premises using AWS Outposts. And I'll actually try to add these links into the offline recording for this and see if we can make them clickable. But I hope I gave you guys a bit of a chance to take some screenshots there if you wanted to as well. All right. Thanks very much for listening, folks. I hope you got this far. I know there's a whole bunch of stuff that we covered, and I'm pretty excited to see what's going to happen in the next 12 months as well. There's going to be a whole bunch of new features there too. But I hope this gave you folks a bit of a rundown on everything that's changed and what some of the VPC architectures would look like with these new features. Thanks for listening, folks. Catch you next time.